first chapter of part 4. Part 4 is mainly about probability. Chapters 13 and 14 are about our specific probability rules that we're going to be learning. Chapter 15 is going to be a little different. It's going to be about random variables. This is going to probably feel completely new to you, as well as chapter 16, which are probability models. So this is certain type of situations that we model with different types of probability formulas. So this beginning part is going to be a little familiar because you've all dealt with probability before, but the last 2 chapters are going to be completely new and a little bit more challenging. Okay, so dealing from randomness to probability, and I've got 13 and 14 combined. The notes are combined, although I do want you to do 13 and then a few practice problems. You don't have to do too many, just the main idea, and then move into 14. All right, so a random phenomenon is a situation in which we know what outcome should happen, like we know the possibilities, but we don't know which particular outcome did or will happen. In general, each occasion upon which we observe a random phenomenon is called a trial. And at each trial, we'll note the value of the random phenomenon and call it an outcome. The collection of all possible outcomes is called the sample space. So the sample space is just a list of all the possibilities that could occur. All right, so there's something that we call the law of large numbers. When thinking about what happens when combinations of outcomes, things are simplified if the individual trials are independent. Now, this is not the first time we've seen this word. It's coming back into play here. We talked about it very roughly on the surface back in chapter 2. Roughly speaking, this means that the outcome of one trial does not influence or change the outcome of another. And that's the basic concept behind independent. The outcome of one trial has no effect or does not influence or change the outcome of another. For example, coin flips are independent. If you flip the coin and it lands on tails, when you flip it again, the coin's not going, oh, I just landed on tails, maybe I should land on heads. The coin pays no regard to what it's already landed on. So flips are independent. Same thing with a die. If you roll a die and you get a 1 and you roll the die again, you could still get a 1. You could get any other number. The probability of getting a number is still 1/6, no matter which roll of the die you're on. So it doesn't matter what you've previously rolled, the rolls are independent. Now that leads us to something called the law of large numbers. And it says that in the long run, relative frequency of repeated independent events get closer and closer to a single value. We call this single value the probability of the event. So for example, we all know that and you need to get used to this notation, okay? You need to be able to read it and use it in your own work. The probability of heads, probability of flipping a coin landing on heads is 50% or 0.5 or 1/2. Doesn't matter how you write that. These all mean the same thing. Now, what that means though is on any given flip, there's a 50% chance of getting heads. So let's say I flip the coin and I've got tails, tails, tails. You might be thinking on the next flip, oh, it's got to even itself out. It's going to be heads this time. But on the independent concept means on any given flip, there's always a 50-50 shot. The even out concept that you're thinking of is in the long run. In the really, really long run, we would expect to see 50% heads and 50% tails. Not in the short run though, not on just a single flip. That's always expect just a 50-50 outcome. The non-existent law of averages. So a lot of people confuse the law of large numbers with the law of averages. Relative frequencies even out only in the long run. And this long run is really long. In fact, it's infinitely long. Infinitely long. The so-called law of averages, that an outcome of a random event that hasn't occurred in many trials is due to occur, really doesn't exist at all. So this is what gets a lot of people in trouble at the casino, If you know anything about roulette, you spin a little ball, it lands on different colored numbers, and you can bet on red or black. There's many different bets you can make, but up on the board, it shows you all the numbers that have occurred. So it should be 50% red, 50% black. So on the board, when they see a bunch of red numbers appearing in a row, they start putting all their money on black because they're thinking, oh, it's got to even out. But remember, the evening out that we should see is in the really long run. This is not anywhere close to a long run. So yeah, you will start seeing some blacks, but don't be fooled in thinking, oh, next one's got to be a black. The actual probability of the next one being black is still 50-50. That has not changed. Even if there would have been a bunch of blacks, the probability the next one's a black, still 50-50. All right, so in some of these cases, it's been equally likely. Like, it's equally likely to get one of 6 outcomes on the die, and it's equally likely to get heads or tails from the toss of a fair coin. However, keep in mind that events are not always equally likely. A skilled basketball, for instance, has a better than 50-50 chance of making a free throw. Let's look at what probability is in some of these cases. The probability of an event is the number of outcomes in the event divided by the total number of possible outcomes. Written in formula-like way, probability of A, event A, is the number of outcomes in A. It's the number of ways A can occur divided by the total number of possible outcomes.